Good day, everyone. This is Module 6B, and I will be discussing the iterative methods in linear algebra. This also includes the eigenvalue algorithms to solve your eigenvalue problems. All right, let's start. Okay, these are the methods enumerated for the iterative solutions of linear systems. We have the Jacobi method and the Gauss-Seidel method, but for this content, I'll just start with the Jacobi method. Just for a recap, when we say linear systems, these are a system of linear equations uh, as a set of m equations with n unknowns. Okay, so you have m equations and we're solving for n different unknowns. They are called linear systems because all unknowns are of power 1. Okay, as you can see from this example, we have here m unknowns, right? Okay, m equations. So as you can see, b1 until bm, yung mga, yung mga ano niya, index ng ating coefficient b starts with 1 until m. So we have m equations and n unknowns. Yung unknowns na yun, yung mga x dito. So we have x sub 1 until x sub n. So we have n unknowns and m equations. Okay, so these a coefficients, constant coefficients, are uh, labeled as a, I, j, where I is your row and j is your column. Okay, and then x sub I is your, or x sub j is your unknown. Okay, and b sub I are your constants. Okay, so we can rewrite this linear system into a matrix. As you can see, the matrix of your constant coefficients a sub I, ij, composes this uh, matrix A. Okay, this is a square matrix. Okay, no, it's not. So sorry, it's not a square matrix. Okay, and then X is your unknown matrix composed of your x sub 1 until x sub n and your matrix of constant B. Okay, so again, A is your coefficient matrix. This is an m by n matrix, and then your X matrix is your unknown matrix with n uh, elements, and then your um, matrix for constants B is your matrix B with m elements, okay, or m rows, right? Sige. From your CE24, we have different direct methods, okay, analytical methods to solve for uh, these linear systems. We have the Cramer's rule, inverse method, until the Thomas algorithm. Okay, and these direct methods solve the problem by finite sequence of operations. Okay, and you get the exact solution. But this time, in CE25, we'll be solving these linear systems using an iterative method where we use an initial guess and generate a sequence or an iteration to provide or to get an approximate solution to this system of linear equations. Okay? They are actually used when yung convergence or yung solution madaling mag-converge. So meaning, or isang uh, condition for that is we have a large main diagonal entry. Okay, so we'll discuss that later. And when the matrix has many zero elements. Okay, these includes the following: Jacobi method, Gauss-Seidel, and your SOR method. Now let's focus first, or let's discuss first itong diagonal dominance na sinasabi rito. When we say a square matrix is diagonally dominant if sa bawat row natin, yung magnitude ng diagonal entry is larger than the sum, or larger than equal than the sum of the magnitude of all the other non-diagonal entries. So in symbols, in absolute value nung diagonal entry, a sub I, di ba? Same number, same yung row and column number kapag nasa diagonal ka ng matrix. So, yung magnitude niyan dapat greater than or equal sa sum ng lahat ng non-diagonal coefficients mo. Okay, for all I. So, yung square matrix natin, diagonally dominant kapag follow nyo tong rule na to. Okay, we have here some note na diagonally dominant uh, matrix or matrices are ensured of convergence for both Jacobi and Gauss-Seidel method. Okay, so as long as diagonally dominant yung matrix A mo, magkakaroon ka ng uh, convergence or sure ka sa convergence, may makukuha kang solution. Pero kung non-diagonally dominant yung matrix, it will not ensure divergence. Pero what you can do is to rearrange yung matrices natin, okay, yung rows, so that maging diagonally dominant siya. You can do that, okay? So some example is this matrix. So yung diagonal entries natin are 4, 6, and 7. Okay, as you can see, yung 4 na yan, that's greater than 1 plus 1. So it's okay. Yung 6 dito sa pangalawa, that's greater than 2 plus 1. Diba? And yung 7 dito sa last row is greater than the sum of 1 and 1. So okay din yan. Meaning, itong matrix of numbers na ito, square matrix na to is diagonally dominant. Okay? Now, we have a notation here for our iterations. We have uh, the notation for our unknown variable x. Yung subscript I natin, that's our ith variable. Di ba meron tayong n unknowns? So, pang ilang unknown siya, siya yung I. And then k is pang yung number of iterations. So, let's say we have x sub 1 raised to 3. Ibig sabihin yan, the first unknown, x, during the third iteration. Okay? Now, let's continue with the first iterative solution or iterative method for system of linear equations. We have the Jacobi method. Okay, pag sinabing Jacobi method, it's an algorithm determining the solutions of diagonally dominant system of linear equations. So we have here, it's actually called iteration by total steps kasi lahat ng iteration natin nanggagaling yung succeeding values niya from the previous iteration. So, totally from the previous iteration. So, step by step talaga siya. So, each diagonal element is solved for, okay, yung diagonal lang talaga yung target na i-solve, diagonal element, and then approximate value is plugged in. Okay, the process is then iterated until it is converging. Okay, this is the main equation for the Jacobi method. Actually, nanggaling lang siya dito sa dun talaga sa summation lang, di ba? Summation of A, ij, this is your coefficient, and then your unknown, equals B sub I. Aj equals 1 to N. Alright, so this one, ang galing lang yan dyan. So, yung summation ng lahat ng A, sa isang row ha, for one row, yung summation ng ating what we call this, coefficients, product ng coefficients and unknown is equal to your B. Di ba yun yung pinaka-equation talaga na sinasolve natin per line, I mean per row. Okay, so, paano siya naging ganito? Ano na lang, in-isolate lang yung diagonal element, di ba? Yung AII. Okay, times x sub I. Okay, nilabas lang yan. So, wala na siya dito sa loob, kaya excluded na siya dito. When j is equal to I, inalis na. So, yung nasa loob dapat nitong summation, hindi na kasama yung j equals I. Kasi alisin na natin si AII, di ba? Okay? So, from there, magiging x sub I, di ba? AII, okay, x sub I is equal to, ilalabas natin to sa other side, so magiging minus is b sub I minus ito. Okay? Tapos, divide by a sub ii. Okay, matitira si x sub I. Okay, so meaning, the next iteration, okay, yung next value ng ating unknown x, okay, for the succeeding iteration is computed using this. So meaning, kunin natin yung sums nung lahat nung product, okay, ng ating coefficient and unknown, okay, initial values ng unknown, x, okay, and then subtract from b sub I and then divide by a sub ii. Okay, you'll see how this is applied sa ating sa example later. Okay, pero yan yung main equation natin. Okay, and some books actually use this ano, uh, modified form ng ating Jacobi method. Okay, di ba? Wherein sinama niya na yung I equals J sa loob ng summation dito. J equals I rather. Okay? Tapos may nilabas siya dito. Basically, ang nangyari lang dito, uh, ginagawa niya lang relationship between yung current solution natin and yung previous solution. Diba? Current solution, previous solution, tapos itong, this is considered like a residual. So kapag close to zero na itong value nito, nagko-converge na tayo dun sa solution. Okay, sa actual or sa uh, exact solution. Okay? So, pero ang gagamitin talaga natin sa implementation ng code, ng implementation ng Jacobi method is this relationship. Okay, the next iteration is computed using this equation. Right, now, this is just an example or a sample algorithm where we can apply yung Jacobi iteration or Jacobi method. Okay, so pwede rin namang other algorithm you can design your own, but it's just an example. Now, we apply, sige, para mas madali natin mag-gets, we apply the Jacobi method to determine the approximate solution for this system of linear equation. We have for x sub I, x sub 1 minus x sub 2 minus x sub 3 equals 3, and negative x sub 1 plus x sub 2 plus 7 x sub 3 equals negative 6, and negative 2 x sub 1 plus 6 x sub 2 plus x sub 3 equals 9. Okay, we first create or form our matrices. Okay, so yung matrix A natin muna is the matrix of our coefficients or constant coefficients. So, yung matrix A natin is 4, negative 1, 2, negative 1, 1, 6, and negative 1, 7, 1. Okay? So, is that diagonally dominant? Okay? Check muna natin. So, 4. Okay, we write our matrix A. Sorry, sumobra. So, our matrix A is 4, negative 1, negative 1, negative 1, 1, 7, negative 2, 6, 1. Okay, hindi to diagonally dominant kasi as you can see, si 1 dito is less than the sum of 7 and 1. So, what we can do is to change or interchange yung position ng second and third equation so that our matrix A becomes 4, negative 1, 1, negative 1, negative 1, negative 2, 6, and 1, and negative 1, 1, 7. Diba? This time, yung matrix A na natin diagonally dominant na. So we can now apply yung Jacobi method. Right? So let's do that. That's our matrix A na. Okay? And then we solve for the diagonal element using the corresponding equation. So yung first equation natin, okay, we solve for x sub 1 from there. Okay, we have x sub 1 equals, okay, ayan, as you can see, diba, pinagpalit niyo yung second and third dito. Okay, para maging diagonally dominant yung matrix A natin. Okay, now, diba dun sa equation natin, if you recall, ito yung main equation na gagamitin. Basically, kukunin lang talaga natin si x sub, i-isolate lang talaga natin yung, what do you call this, diagonal term. Diba? For x sub 1, lilipat natin itong dalawa sa kabila. Okay, ito yon. Okay, so that becomes 3 plus x sub 2 plus x sub 3. Okay, and then yung coefficient na x sub nung diagonal matrix, diagonal element natin, which is a sub I, so sa case na to is 4, yun yung gagamitin natin dito. Kaya may over 4 dito. Okay, si b sub I is si 3. Okay, so 3 plus x sub 2 plus x sub 3 over 4. So this is actually this for the first equation, for the first row. Okay, for the second row, ganun din. Iwan lang natin si 6x sub 2, lipat yung dalawa sa kabila. So we have 9 plus 2x sub 1 minus x sub 3 divided by 6. And finally, for the third row, iwan natin yung diagonal element 7x sub 3, lipat yung dalawa sa kabila. So we have negative 6 plus x sub 1 minus x sub 2. So divide both sides by 7, we have this equation. Diba? So ito na yung magiging main equations natin to solve for the succeeding guesses for the x sub 1, x sub 2, and x sub 3. Okay, and itong mga to, they will all come from the previous iterations. Okay, kaya k ito. Diba? Ito yung k sub k plus 1. Okay. Previous iterations yung nasa right hand side. Alright, so let's just rewrite this and form a table. X sub 1, x sub 2, and x sub 3. Okay, so iterate in total steps yung tawag kasi nga first step nanggagaling lahat sa previous step yung previous values. So let's say we have an initial guess na puro 0. Okay, initial guess natin sa iteration o sa iteration number 0. So 0 lahat yung initial guess natin for x sub 1, x sub 2, and x sub 3. Now we substitute each value ng x1, x sub 2, x sub 3 na to dito sa bawat isa to solve for the succeeding values or sa succeeding guesses. So, sa x sub 1 na to, substitute natin si 0 and 0 and 0 dito. So, we have 3 plus 0 plus 0 over 4, we get 0.75. Tama. Okay. And then for x sub 2, we have 9 plus 0 minus 0 divided by 6, we get 1.5. So, tama rin. And finally, kay x sub 3, we have negative 6 plus 0 minus 0, that's negative 6 over 7 or negative 0.85714. Okay? Tapos sa error, mga error dito, yung values niyan are computed by getting the absolute error. Okay? Meaning, yung previous value and current value ng bawat unknown variable x natin, sasubtract natin and get the absolute value. So, parehas lang naman yan. So, it's 0.75, 1.5, tsaka 0.857. And then we just continue. For the third iteration, or iteration number 2, substitute natin yung previous value ng x sub 2 and x sub 3 dito. So we have 3 plus 1.5 minus 0.85714 plus divided by 4, we get 0.91071. Okay, and for x sub 2, substitute lang natin 0.75 kay x sub 1 and yung negative 0.85714 dito kay x sub 3. And then we get this, and so on and so forth. Okay, yung absolute error natin, so kay error 1, difference lang dito, absolute difference nitong dalawa, that's 0.16071. Ito naman 0.039286. Itong dalawa naman is 0.10714. Okay, we just repeat that until we arrive at the maximum number of iterations. Okay, or if yung error criteria natin ay na sunod na or na yung na-specify na tolerance for the errors are satisfied. So we terminate the iteration when all errors meet the tolerance value, or kay lahat dapat lahat ng to check natin, or yung maximum number of iterations is already reached. Okay, so yun na. So ang final natin dito, so sa case for example, ang ano lang niya is 0.0001. Okay? Kailangan less than that yung mga errors niya. So, okay na to. So, tumigil siya after 10 iterations. Ito na yung mga guesses natin. Okay, ito na yung approximations natin for the unknown variables x sub 1, x sub 2, and x sub 3. Okay? So, that's the simple application for the Jacobi method. For the next content, I will be discussing yung Gauss-Seidel method naman. So, for now, thank you and goodbye.